Hello, my name is Michael Bucaro. Today I will be walking through my model of the St. Croix Imperial fly rod, the 9-foot 5-weight model. So here you can see its resting height. It didn't really deflect much without a load because it is a very light material and hollow on the inside, right? Here you can see it overloaded. So we tried to load it with a 1.2 pound rock. This is just tied onto the line, right? We tried to load it with a 1.2 pound rock. That didn't work. It didn't leave it deflected too much. It was just stuck on the ground still. It can lift this weight. It was stuck on the ground. So here we went with a 0.3 pound rock, which is almost on the ground, but not quite. You can also see the eyelet there. That eyelet will be important. You can see the line kind of resting. You can see the line resting against it there. It's kind of hard to see because it's not quite in focus, but the fly line is really small, but resting against it. Actually pretty good as a point load actually because it's so small. Now to the actual model. This model is two parts. The first is the actual fishing rod. This is made of 4 sections. One section is shorter than the others because that's the base of it. That's just kind of what it is in real life. So 4 sections, varying. You'll note that we'll get to that in a second with the segments. But 4 segments for the fly rod, and then for the eyelet, just a lot smaller than the fly rod. We have attempts. We have this is the eyelet. It's based off of the measurements taken from the actual eyelet. This is a shell revolve, 2 shell sweeps, and then 3 or 4 total shell lofts. But I only did 1 shell loft. I only made this side, and then I mirrored it to get to work. And then I filleted the edges here, just for like stress concentration purposes. And then to the property section. So this. Let's do the rod first. The rod is made of, or modeled as, it's a model is carbon fiber. So that's the density, it's the elasticity, Poisson's ratio 0.3. The Young's modulus is very high. It's based off of the actual to get this to match the actual deflection measurements for a static case, because there are some assumptions and inaccuracies made here, so a higher Young's modulus is needed to compensate for that. First, obviously, is the geometry. The actual rod is tapered pretty evenly in terms of, it looks like, thickness and radii. That's an assumption. So to make an assumption for this, that did be constant in radii and thickness, so I averaged from the base, and I can only get 1 radii measurement per segment at the base of it because that's where the opening is. So that's likely an inaccuracy. Also, I assume that this is an ice chalk material. This is an ice chalk material, right, carbon fiber. So that means, for people who don't know, it will behave differently in different directions depending on how you act on it, or when you act on it. So you're going to get varying properties, which can also make it appear thicker or appear stiffer in certain directions than others. So we're using a very high Young's modulus to get to match the actual behavior we saw. I don't always keep saying we, it's just me. The eyelet is made out of shell elements. It's made out of steel, or soon to be steel. So the density and then the elasticity, just steel. Pretty standard for that. Here you can see the sections. So I had to do several sections of the shell elements, but it's like, they have the proper thickness. And then for the rod itself, I don't know why it keeps unfocusing. For the rod itself, we have, I'll be probably based on the profiles. You can see this. A lot of these measurements were taken imperial because this is made in imperial and then converted into metric. So everything you're seeing is a metric. And then the assembly. So in the assembly, you can see the rod then joins to the eyelet. Notable that in real life, this are the same radii, but because, once again, this radius is an average of that radius is an average. It's going to be a little thicker there. It's kind of the truth for the entire thing. And you can see once again, it is a hollow pipe. Yeah, hollow pipe. And then for the step segment, we have a static step and a dynamic step. The dynamic step is 5 seconds long, millisecond increments, 10,000 max seconds. You see enough, right? For the interaction, the two parts are, I use a tie constraint. See it down. Past it. No, that's it. It would be right. Yeah, so you can see it's just a tie constraint done on this between like the tip of that node, and the bottom surface of this. And then for the loads, things get a bit more interesting. So for the actual load itself, we have a simple load based off of this load is based off of the weight of the load that you see in that picture. So that's the load. Easy enough, right? That's just your load. Going downward. And then for the boundary conditions, so the first boundary condition we have is primarily in the static step, right? Or only the static step and the initial step, which we fix the handle here of the rod in place. That gets deactivated for the dynamic step because we were rotating this portion. And the way this rotation is applied is, so, it's just a displacement boundary condition, and then you have to use the amplitude. So you can either use this create amplitude button or come over here and double click amplitude. And you go to the amplitude. So if you actually do this, the amplitude creation screen looks like this. I chose equally spaced. Do what you want. And then you choose your interval, so half a second, and then it goes from 0 to 1. And that is about 60 degrees of rotation in radians. And then the last boundary condition is we fix this base node in place, otherwise it will just fall through space forever. Not very useful to have. Then from there we have our meshes. So the rod is 16 elements. It's 16 elements. It's just a rod. Its model is just beam elements. If I go here, you can see they're just B33, 2-node cube beam space, right? Cubic formulation, as we learned in class. And then for I'll do the mesh query for people so they can see the mesh query. You can see 16 linear elements of type B3 there, right? And then for the eyelet, you can see most of the elements for this one are in this little thin segment here, which makes sense, right? A lot of elements to mesh this whole thing properly. This is a lot less dense in terms of element meshes. I did try to do partitioning, but it's not the prettiest mesh, but it works because this part, because of where it's at, experiences the lowest deformation and the lowest stresses, which you'll see in the results. So even if there's some malformed elements like there are here, it doesn't end up impacting the results too much. I wish I could have fixed those, but that's the best I could get. But it doesn't impact the results too much. So, And then for the actual visualization segment, so we'll start with the static case. So it starts out statically loaded. Oh, wait, I have to do, this one's the actual room. It starts out statically loaded. I forgot to actually wait really quickly. This mesh is also very heavy mesh. It is 752 nodes and 16 elements. So as you can see here, it deflects downwards by, let's do the deflection for you, by around 7.068 meters. 0.8481 meters, which it's a pretty decent deflection. That actually comes out to, I think, it came out to pretty much pretty spot on to what the actual real life deflection was. And then the dynamic case also, you'll want to note, because there's some trends that remain true even in the dynamic case. The highest stress is between where the thin segment meets the big segment, which makes sense. If the lever action, if like the moment arm is the same here and here, so they're experiencing the same moments, but the area on this is significantly smaller, then you're going to see a higher stress, right? Makes sense. You'll want to note that for the dynamic case, you'll see in a second, the lowest stress will be in the. So you want to note here, the lowest stress is going to be in this segment, right? Matter of fact, it's so low that if you want to visualize it, you need to go here. Then you need to go to specify, and then take whatever the go like 4.378, then like E8, or even go down one even from there. Yeah, that'll let you. Oh darn it! Yeah, rotating this is impossible because nearly impossible because how long it is. So you'll see the higher stress regions are going to be right where the force is applied there at the tip. This arm there. Just make it a little bit. Yeah, that force. So right where it's applied, the thin arms here, and the base where it connects. This makes sense, right? So these are thinner segments, and you actually have a moment on them, and it's right where it joins too. So you have stress concentrations at these corners, and obviously right where the force is being applied, and then a little bit where it contacts the actual beam. But once again, the lowest stresses is in the entire thing. Sorry, the recording software glitched, and part of this didn't get recorded properly. So there's going to be a cut in the video. You're going to go to where I'm displaying the movement of the rod. Yeah. So you can notice it comes up. It begins jerky as it comes up. But yeah, so jerks as it comes up. It achieves its max, the final displacement of this rod base here at half a second. And then it'll continue to oscillate, or it continues periodic motion forever. Yeah, which this can be observed in the graphs for it. So if you want to look at the very tip of it, you can see the jerkiness up here, and then the continual periodic motion. This gets, so that's like for the end. It gets, this amplitude is greater the farther away you get from the base. Like this is just the midpoint of the rod. You can kind of see a little bit of the step action there, and then the oscillations, but it's a lot less when you're not at the end of the rod. Makes sense, right? This model was also verified independently with an FEA solver I made for separate reasons. That one is designed for hyperelastic materials and dynamics, but for this one we only did a static case because the dynamic case wouldn't converge. There's some of the code for it. Yay, whatever, right? This is the mesh for it, or one of the meshes. This is the 287,000 element mesh, and that's 53,000 nodes. So a lot denser mesh versus 16 to model this rod portion. This model can only support a single material, so only the rod is modeled in it just to test the deformation. You can see that this is a lot denser of a mesh, right? Very cool. This is also actually tapered, which is neat, but it's made of tetrahedron elements, so they don't actually model bending, so they're significantly, so to approach the same level of, so like they don't actually bend, so you need a lot more of them. Like a lot more of them. And the actual results for that end up looking like this. 6.4 meters, or 0.64 meters, which is pretty close. It actually, I did run one with this even denser mesh than this, and the more elements you add, the closer it gets to approaching the beam elements, which makes sense, right? 'Cause you need more to approximate it. Yeah, that's this model, and we'll just go back and watch this video. Oh, let's go back to, we want to see the actual, let's go back to the video one more time, because yeah, this is the once again, it's modeling a hook set of a trout. So you know, quickly in half a second, pull it up. The video makes that half a second look a lot slower than it is in real life. I timed myself to see how fast I actually do hook sets, and it came out to anywhere between like a second to a quarter of a second, depending. So half a second's a good medium. And then yeah, it will just, you gotta sleep forever. Yeah, model.